Yes. So please ask.
Yeah, sir. My question was that should we design a single bit cell or a array of bit cell? Uh,
So you have to, as a class, you have to design memories. So you will be designing a full array of memory cells along with end cells, edge cells, everything, and not just one bit cell.
okay, so sir, what I was trying to ask is like, for example, if I take the 60 SRAM cell, so in that also have to design an array.
Whether you take a 60 SRAM cell or an 80
Or
SRAM
okay,
cell or whatever, here we are designing a memory. As a class, our goal is to design a memory. So no single memory cell. It is always an array. Even when you're talking of designing IOs, it is about designing an array of IOs. You know, so many IOs at distant placed next to each other so that bit lines can directly come and enter inside the IO.
okay, sir, got it. Thank you.
Yeah. So, bas, that was the only question someone had. Which projects are you worried about? Which ones are not clear to you? Are all the project titles clear to everyone?
So can you talk about the replica one? What exactly is that?
Okay. So replica path we will cover in the class tomorrow. Replica path is basically okay. So we understand that we need SAEN signal, the activation signal for the sense amplifier. All of us realize this.
Yes, sir.
So how will you get that signal? Such that and you want to get that signal always at a time when you want to get that signal at a time when your how do I put it? You want to get that signal at a time when your sufficient offset has been generated at the at this level. Am I right? Okay, whiteboard. I'm just opening my whiteboard so that I can explain it to you. So you want to do it when there is sufficient differential that is generated at the sense amplifier inputs. Are you with me?
Yes, sir.
Yes, sir. So what we do is, okay, let us say this is the entire memory. So clock comes from here. It goes to the clock generator here. One clock goes to the pre-decoder. Another clock goes to the IO region, turns off pre-charge. This results in generation of word line. Then let us say this word line leads to generation of a differential on the bit line pair. You want that another signal SAEN should come and trigger the sense amplifier only after sufficient differential has been created. Is the problem statement clear?
Yes, sir.
Yes, sir. What is the worst case arrival time for, or what is the worst case at which offset will be created for any sense amplifier? Which sense amplifier will probably have the worst case offset? There are sense amplifiers all over the memory, है ना?
Which is far from the decoders or something.
So then you are saying that this particular sense amplifier will have the worst case offset. The farthest one.
Yes, maybe.
Okay, let us assume that this has the worst case because, and the logic that we use is that, okay, word line selection will be last for this one, for the memory cell placed here. So since word line selection happens in the end, the differential creation starts in the end. So this sense amplifier has the worst case offset. At any given time instant, say 200 picosecond after CK, this sense amplifier will have the minimum offset. So what you want is that offset that enables signal for this sense amplifier may come early, but for this sense amplifier, it should come at, let us say, 450 picosecond when it has sufficient offset available at it. Are you with me?
Yes, sir.
So what is done is, to be able to do this right, what is done is, we say that we will track the word line. So see, again, in a smaller instance, suppose the instance size was only this much. I wanted the sense amplifier enable to come at, let us say, 350 picosecond. But when the memory instance is a big one, then I want it to be later. If the memory instance was still smaller, it can come at even 250 picosecond, and so on. So I want there to be some dependence on memory size. Depending on whether the memory is big or small, the enable signal should come soon or late.
Yes, sir.
So what we do is to track the RC. So how do you get the semblance of memory size? You track the RC of word line and bit line. And when RC of either of them increases, you know that the instance is either very wide or it's very tall or whatever. So to be able to do this, what you do is you create what is called as a replica path. Now, what is a replica path? A replica path is an additional word line and an additional bit line at the end of it. So come to think of it, and this word line, replica word line and replica bit line, are always selected. See, depending on address, sometimes this word line will be selected, sometimes another word line will be selected, sometimes another word line will be selected. But replica word line will always be selected. So what happens? Whenever there is a read operation or a write operation, the word line will be selected and the replica bit line is also selected. This word line also goes to multiple cells on the replica bit line, so that more than one cells can discharge. Okay, and the replica bit line then discharges and generates SAEN.
Sir, this path, replica path, is representing the worst path, like the more RC path.
Yes.
And why we need to discharge more cells? Why not only one?
Okay, so the SAEN that you need over here is a digital signal.
Yes.
But the bit line, you are only discharging for, say, 100 millivolts.
Yes, depends on offset rate.
Yeah, let us say 100 millivolts.
Yeah.
So if you set up only one memory cell over here, the replica bit line will also discharge only by 100 millivolts.
Yes.
Then how will you generate the digital signal? If you say I put a sense amplifier, then what will trigger that sense amplifier on the replica bit line? Cannot be done, no? It becomes a chicken and egg story. So only the replica bit line, you say, will discharge fully. It will go from VDD to almost 0, or let us say less than VDD by 2. So what happens? You put an inverter beneath it. As the replica bit line goes to lower than VDD by 2, the inverter generates SAEN signal. Now, to be able to bring about this discharge of let us say 600 millivolts, when actual bit line is discharged only by 100 millivolts, you need to select at least 6 memory cells here.
Yes, sir.
That is why multiple cells are to be selected.
The motive is we have to bring SAN before this 100 millivolt is discharged in the worst cell, right?
Yes, we want that. Whenever this happens, whenever sufficient discharge is generated, then only then SAEN should come.
Sir, I didn't understand. If from the replica path, if we are generating 100 millivolt, what's the issue? Will it not trigger a sense amplifier?
How will you trigger the sense amplifier then?
Means we just have to give the gate voltage to that NMOS or something, right?
Yeah, but then there is an
Repurpose.
activation signal. Na? SAEN will be needed for the sense amplifier there. How
By
will you
means
get
of
that?
this, by means of just discharging one cell, 100 millivolts,
Mhm.
the that I can use for the triggering, right? Why do I need the 600 millivolts here?
So if
That
you could trigger with only 100 millivolts, then you do not need an SAEN at all. You will, as soon as 100 millivolts are discharged, you trigger all the sense amplifiers. What's the big deal?
yes, sir.
You can do it, na? Then there is no problem. The problem is that the typical conventional latch type sense amplifiers that we have, they need an SAEN signal which is digital in nature, which goes from 0 to VDD. That is when the tail transistor will sink sufficient current to trigger
Okay.
something.
So the digital it's a 1 volt and 0.6 is differing between 0 and 1, right?
Yeah.
Now got it.
Okay.
Sir,
So
related
this is
to
again,
passive.
0.6 is just a representative number. You may say that I want to discharge it by 1 volt or by 0.9 volts, and then you will say it will trigger the sense amplifier.
Sir, related to bit the SRAM cell, we have 8192 words, right?
Mhm.
Words or so that many cells we have to create in if you choose the SRAM.
No, we have 8192 words. Each word is 32 bits wide. Am I right?
Yes.
So how many words, how many bit cells, what is the memory capacity then?
We have to multiply it.
हाँ तो बताओ. 8K cross 64. What is 8 into 64? Hello? The 2 raised to
5
power
and
n.
2.
हाँ, the 2 raised to power n वाला चीज यार. 5 and 2K is
Yes.
equal to 0.5 MB. That's the number. So you need to make 5 and 2K cells.
So we have to just make a one cell and then copy it and flip it in the BDD or ground rail, right? In terms of layout, if I ask.
You make one cell, you flip it. So
Do we have any tool or do we have to do it manually, sir? Like this many cells?
So you can use the skill programmation inside the Virtuoso tool to do it. You can use, so you use Virtuoso. You used skill scripting.
No, I didn't.
Okay, so let us learn that. It's a good thing to learn. So in skill, you can actually write programs so that you can tile cells next to each other, and you can make arrays of. So you just make one IO, you flip it. So you make IO, flip it, and then this one block you can repeat as many number of times, let us say, so that you have 10 IOs or 22 IOs or 32 IOs and so on. And this can be done simply by one command in skill. So it's a good opportunity to learn skill. Cadence के साथ उसके manual में दिखा जाएगा आपको.
Okay, sir. Thank you.
Okay. Yes. Any further questions?
Hello, sir.
Yes, Harshit.
Sir, in the design IO circuits project, we have to design pre-charge, write driver, and multiplexer. And there is a separate project on write driver. So how are these two different?
So let me have a look. There might be a mistake. Just give me a second. So in the IO design project, pre-charge, write driver, and multiplexer. So the separate one for write driver is about negative bit line write driver. The one that we're talking about over here, it is a regular right driver. Okay, it does not generate negative bit line. But the separate right driver project that is listed there is about the negative bit line. So the negative bit line will also be generated there. It requires additional design of a charge pump and so on.
Okay. So, like what we studied in class, right driver would be implemented in that IO circuit part, and negative bit line voltage would be that in right driver circuit part.
Yes. So again, the constraint for the negative bit line right driver guys would also be that they have to match the layout in such a way that it can be used in the IO that you design, that the IO team designs. So they can simply remove the right driver of their IO and plug this one in. That is the intent. Okay, there would be some increase in area, that's fine, but it should be doable.
And sir, what were you talking about charge pump in this particular project?
Okay, so when you come to talk about negative bit line right drivers, so or when you need to generate a voltage which is higher or lower than say higher than VDD or lower than ground, then we make a kind of a charge pump circuit there. Now I'm just giving you a sample circuit. It does not mean that yahi circuit hai. So let us say this is my bit line. On bit line you put a capacitor which is coupled to an inverter on the other side. So what you do is you, through the right driver, right signal, discharge the bit line to 0. So WRDRV goes 1, BL discharges to 0. This happens. After BL has discharged to 0, so when you do that, at that point of time, this NBL signal is 0 initially. Okay, it remains 0. After bit line has gone to 0, so this you do, and then you turn this off, right driver. So you take this high and then you turn this off. Okay, so once you turn this off, what happens? Bit line is now floating. After it has been turned off, bit line is now floating. So now what you do? Now you take NBL signal high. After it has been turned off, you take NBL signal high. NBL high means this X signal, which was initially 1, would go to 0. Are you able to see this?
Yes, sir.
When X goes from 1 to 0, it will couple because it is coupled with the bit line. So now if one side of the capacitor goes from 1 to 0, the other side will also tend to have a similar voltage transition. So now bit line would want to go below 0 volts. Okay, let me remove some of the signals. Let me move them down there. So what happens now is, because X went to 0, from 1 to 0, BL also starts to see, it was a floating node for now, it also starts to go below ground. And that is how you generate NBL. So this is 0 level and this is negative level. Then after the operation is completed, right operation is completed, you again take NBL to 0, X would go up, this would slightly go up, and that is when you also turn your pre-charge on. So pre-charge could be another signal which could go to gates of these PMOSs. So then you turn pre-charge on. Pre-charge on means pre-charge had gone to 1, it would go off now. So will go low now. So that means bit line will get pre-charged to VDD. Now you are ready for accepting the next cycle. Are you able to see this?
Yes, sir. So in this case, whenever we will go to the next cycle, like we are going from negative bit line to VDD. So like, would there be the possibility that it could not rise to full VDD? Like if.
So that is what we have to ensure in the timing analysis, Harshit. We have to ensure that we say that the next cycle, so there is a definition of T cycle. You remember? In the data sheet, we looked at a definition of T cycle there, that there is a T cycle करके time defined होता है memory के साथ, है ना? What does this mean? This means when, so if I gave a rising edge of clock abhi, when can I give the next rising edge of clock? So this spacing has to be ensured such that a bit line has precharged to full VDD. Okay. So precharge on to full VDD delay has to be added and ensure that it is taken care of in the T cycle definition itself.
Okay, so like in that IO circuit part, it is mentioned that BL charge discharge time of 100 picosecond. So this is the T cycle time of 100 picosecond.
No, this is not T cycle time. This is the pre-charge time. T cycle time is first rising edge of clock to the next rising edge of clock, which means it includes word line selection, all those delays it would include.
Okay, got it.
Okay. Who next?
Sir, in read operation, we don't discharge it completely to 0 because of sense amplifier, but in write operation, we have to discharge it to completely 0.
You have to take it to a negative level.
Even negative level.
Right as a scheme, na?
Yeah.
Because we want to write a 0. Unless we discharge it to 0, how will we be able to write 0 onto the internal node of the memory cell? है ना?
Yes, sir, got it.
Yeah. पूछो. So are all the other project titles clear to you?
Sir, can you talk about like how do we meet the offset voltages? Like, do we have to do any calculation or something?
How do we meet the offset voltage requirement?
Yes, in the sense amplifiers.
Okay, so how do you estimate the offset requirement of a sense amplifier? Do you know this much?
Requirement, I know that there is a need of offset that I know, but I don't know how to judge it. Yeah.
So there are two questions then, Moin, that you are asking. You're asking,
yes.
First question is, how do I estimate the offset requirement of my sense amplifier? And then the next question is, how do I ensure that when SAEN comes, that is met?
Yes, sir.
Am I right?
Yes, sir.
So I would recommend कि ऐसे ये जो सेंस एम्पलीफायर का ऑफसेट रिक्वायरमेंट मेजरमेंट का जो सेटअप है या जो तरीका है, that you check with your seniors. Can you do that?
Okay.
Not the TAs. I want you to interact with your seniors. There is a reason behind that, but can you do that? Are you open to doing that?
I will try.
So basically, let me give you a top level overview. You will need to run Monte Carlo simulations. And you will then need to look at the statistics of those Monte Carlo simulations in terms of mean and sigma. And then we will estimate mean plus 3 sigma and mean minus 3 sigma offset requirements of the sense amplifier. Okay. So what do we simulate? What is our stimuli in that Monte Carlo simulation? For this, I want you to talk to your seniors. Okay.
Yes, sir.
Now let's come to how do we measure the offset of how do I ensure that the offset that my sense amplifier has when SAEN arrives is sufficient. So for this, what we do is we actually make a critical path or a replica path for the critical path. जहाँ पे हम क्या करते हैं मोहन? We make dummy word line, so and dummy bit line. Dummy matlab replica bit line, and we design the inverter at the end of the dummy bit line, buffers there, and this is the enable signal. Okay. So what we do is we measure, we make a circuit which only includes this kind of a path, nothing else. Okay. And we measure the delay of this path. And then on this path, we run Monte Carlo. So what would we get? We would get a delay path. We would get a distribution of how, at what time my SCN will arise. So this will be time. This is number of samples. So you will get at what time my SCN will arrive fastest. Let us say 300 picoseconds is the fastest arrival of my SCN signal there. Are you with me? यहाँ तक समझ में आ रहा है?
Yes, sir.
So then you say, okay, if 300 picosecond is my SCN arrival time, in a separate simulation, what you can do is you can model a memory cell, the load of the entire bit line, and the load of the sense amplifier. And then you say, I will trigger the memory cell with a word line, and I will measure the differential created on the bit line at 300 picoseconds. Okay, I will plot that. You see, there will be a plot of that also. Over here, this will be VDIF, and this will be number of samples. Are you with me?
Yes, sir.
I have to ensure that the minimum VDIF, or let us say nominal minus 4 sigma or 5 sigma, is greater than the sense amplifier offset that we talked about here. Okay. So we will discuss this tomorrow in the class also. This is called self-timing analysis. Fine.
So what is the green curve signifying?
Green curve is signifying the delay at which SAEN will come after word line is selected.
So, sir, here we are doing two things. First, we did Monte Carlo and find the maximum time
Minimum
at
time.
the sample
Earliest time when SAEN can come.
earliest. Okay.
Because that will
And
have the minimum offset, no?
Yes. In the second side, also the minimum, the difference which I get, right?
Yes.
Okay.
This minimum difference should be greater than your offset requirement.
This green part that we are getting from the replica circuit, replica wala?
This is the replica path, huh?
Yes.
That is where I showed now that the word line. So this what I have shown over here is the replica path. This one. This is the replica word line, replica bit line, and so on. So when I showed the replica path over here initially, hello. So in the beginning of the class, when I showed the replica path over here, I had shown that replica word line will go like this and select bit line, and then SAN will come like this. In reality, this means that horizontal delay will come twice. Are you able to see this?
Yes, sir.
So to avoid this, what we do is we actually just turn around the word line after 50% of the word line capacitance. So you take it forward and then you turn it around. So now horizontal delay is coming only once. Okay. Hello.
सर फिर वो नीचे भी जा रहा है ना, मतलब वो
हाँ,
नीचे
but this one can be, so okay, so you can tune it. So first thing is, now all this part is very close to my control circuitry. Now to generate reset, so SAN में आपको लग रहा है कि there is a horizontal delay again, but what about reset? The reset will be generated right away. The memory can start to reset, word line can turn off, everything can happen right away now, because my replica path is right next to the control region, which was not the case earlier.
Yes sir.
To generate the reset, you saw two horizontal signal delays. And until you reset the word line, can you start to precharge the bit lines? No. है ना?
Yes sir.
So you reset so that word lines can get deselected and you can start to precharge the bit lines as soon as SAN comes. Okay. Anything else? Anything from the class? We talked about mismatch yesterday. So we'll talk about statistics and the statistical analysis tomorrow. But anything else pending from the class that there could be a doubt about? Yes, Harshit.
Sir, in the replica column, replica path project, what do we mean by no change in active layer, minimal change in poly layer, and the layout should be as close as to the real SRAM cell layout?
Yeah. तो आपको क्या समझ में आया? When you read this, what did you understand?
So like I understood ki we need to create that worst bit line and worst word line column, and that would basically correspond to SRAM cell layout. But I was confused, like in SRAM cell layout, we need to optimize our figure of merits. So in that case, in this case, do we also need to optimize figure of merits for 60 cell and then create replica column, or just we need to create a replica column and then observe?
So the prerequisite for starting to work on the replica column is that you should have the regular bit cell available with you. Okay. So then in this regular bit cell, so replica column का मतलब क्या है? Replica column का मतलब, so in a regular bit cell you can store 0 or 1. In the replica bit cell, you want the memory to discharge in every cycle. Am I right?
Yes.
So it has to be programmed as 0 or 1, whatever you want to program it as, but it has to be programmed permanently. Are you able to see this? Because it is always, its function is to always discharge the dummy bit line, the replica bit line.
So why this one?
Okay. Why do you put a replica bit cell?
To measure the worst case.
Measure the worst case. How do you measure the worst case?
Like 0 या 1 में, मतलब जब भी हम write कर रहे हैं या read कर रहे हैं, तो इसमें at least read या write हो रहा है या नहीं हो रहा इसके थ्रू?
रीड बिट सेल के थ्रू हो रहा है कि नहीं हो रहा का क्या मतलब है? आप बिट सेल के लिए वर्ड लाइन ऑन करोगे तो बिट सेल तो डिस्चार्ज करेगा ही, तो रीड तो होगा ही होगा. अभी हमने रेप्लिका बिट लाइन के टर्म्स में क्या देखा था? We said replica bit line will discharge to VDD by 2 or lower so that the SAN signal is generated. तो वो तो होगा ही होगा. But the thing is, there is a replica bit line, let us say here. This is, let us say, your replica bit line. You want it to discharge in every cycle. If this has to discharge in every cycle, what should be stored on this particular node?
Yes, sir. 0.
0. If this stores, if this gate is at 0, will this bit line discharge?
Okay, this is gate. I thought it's a bit line.
The bit line is the vertical one, na? I made the layout.
Okay. No, this should be 1 then, if we are talking on poly.
Yeah. So the poly has to be connected to 1. Now, how do you connect this poly to 1? You know that there is some VDD over here. There is a VDD supply here. There is a VDD supply here. But you do not know how to connect it to that supply yet, because you cannot simply short. If you short, then the capacitance on this particular bit line would start to appear as different from another bit line. So what is typically done is, one thing is, okay, so there is a long contact over here. There is a long contact. There is a long contact between this poly and the active over there. One way you could say is, okay, I will simply create a short between the two of them. But to be able to do that, you will have to cut metal 2 somewhere, metal 1 over here somewhere. So when you will open the layout, जो हमने class में भी देखा था view, you will see that there are metal 1 stubs here, there is a metal 1 stub over here for the bit line, and so on. So it is not easy to connect this metal 1 stub to this metal 1 stub. It can lead to DRC errors there. So what is therefore done is, typically this poly is pulled out, it's stretched out. Okay, and over here a vertical line is run, which could be metal 1 or metal 2, and a contact is dropped so that this node becomes VDD for all practical purposes. Okay, and you do not turn on all the cells. So what happens is, for the other cells which are beneath over here, in those cells, when you pull out the poly, you will connect them to, let us say, ground. Okay. Similarly, the poly over here, the word line of this particular dummy cell or replica cell, it has to be connected to a replica word line. So this also is kind of stretched a bit, and replica word line is brought vertically, and this particular transistor is turned on. It would go down there also, so that if there are other replica cells also, they can also be turned on by the same word line. Are you able to see this? Yeah, OHT हो गया?
तो थोड़ा तो समझ आया, बट पूरा नहीं आया.
आप लेआउट देखेंगे तो आपको समझ में आएगा. अभी आपने लेआउट बनाया नहीं है ना बिट सेल का, आपने खाली स्क्रीन पे देखा है. स्क्रीन पे देखने में और खुद डिजाइन करने में बहुत बड़ा फर्क होता है. तो आप लेआउट को दोबारा से देखें, स्क्रीन पे ही देखें चाहे, तो आपको समझ में आ जाएगा मैंने ये सब क्या बनाया. ये आपको समझ में आ गया मैंने बिट सेल क्या बनाया है?
हाँ सर, ये जो आपने
बिट सेल इज क्लियर. तो ये समझ में आ गया मैंने ये बिट सेल के पॉली को क्यों एक्सटेंड करा है.
यस सर, ये भी समझ आ गया.
क्यों करा है?
मतलब ताकि जो VDD वहां से हम सीधा कनेक्ट नहीं कर पा रहे थे, इसको इधर एक्सटेंड करके VDD प्रोवाइड करना है.
हाँ, अब फिर ये समझ में आया मैंने ये क्या बनाया है.
हाँ, ये मतलब ऊपर जो बिट सेल है या फिर ऊपर जो है उसको मतलब मेटल 1 के थ्रू दूसरे से कनेक्ट होगा, तो उसके कॉन्ट्रैक्ट के लिए बनाया है.
हाँ, देखो यहाँ पे क्या करा था मैंने, यहाँ पे मैंने कहा था मल्टीपल सेल्स हैव टू बी टर्न्ड ऑन रेप्लिका में, है ना. मैंने ये देखा, ये दिखाया था यहाँ पे मल्टीपल सेल्स हैव टू बी टर्न्ड ऑन.
हाँ हाँ,
उनको टर्न ऑन करने के लिए उनकी वर्ड लाइन को ऑन करना पड़ेगा ना.
हाँ सर.
टिपिकली तो वर्ड लाइन हॉरिजॉन्टली दौड़ती है.
हाँ,
लेकिन मेरी रेप्लिका वर्ड लाइन तो ऊपर से आ रही है, उसको वो ऐसे आएगी नीचे, है ना. वर्ड लाइन यहाँ से आई और मैं उसको स्ट्रेच करके नीचे ले जाऊंगा. समझ में आया नहीं आया? ये वर्ड लाइन हॉरिजॉन्टली गई थी, फिर ऐसे घूम के वापस आई, अब यहाँ नीचे जाएगी, तब यहाँ पे रेप्लिका सेल्स को ऑन करेगी ना.
हाँ हाँ, ठीक है सर.
तो मेरे को एक वर्टिकल वर्ड लाइन का कनेक्शन भी देना है, तो वो मैंने यहाँ से दिया है.
ओके,
अब समझ में आ गया?
ठीक है. हाँ सर।
गुड। और बताएं।
सर सेंस एम्पलीफायर में 2 टाइमिंग फैक्टर है, एक सेंस एनेबल टू क्यू लैच डिले एंड पल्स विड्थ। तो ये क्यू लैच जो है ये फॉर जो अपना सेंस एम्पलीफायर के एक प्रॉपर स्टेट आने के लिए ये वाला डिले है ना, राइट?
क्यू लैच मतलब सेंस एम्पलीफायर के आउटपुट को आपने लैच कर दिया, वो डिले। तो याद है हमने सेंस एम्पलीफायर के बाद कहा था कि हम एक 2 NAND गेट्स लगाएंगे जो आपस में लैच कॉन्फ़िगरेशन में कनेक्टेड होंगे,
यस।
है ना? दिस इज सेंस एम्प लैच या क्यू लैच। तो सेंस एम्प ऊपर है, सेंस एम्प इज अप देयर, उसके बाहर यू हैव टू मेक अ लैच। तो यू कैन मेक अ लैच लाइक दिस, और व्हाट कैन आल्सो बी डन इज, सो ये आप, सो दिस इज अ वेरी गुड ऑफिस आवर्स बिकॉज इसमें आप पूरे वैरायटी ऑफ पेरिफेरी सर्किट्स का डिजाइन समझ रहे हैं मेरे से। आई एम वेरी हैप्पी। तो क्या होता है देखो, सेंस एम्पलीफायर से आपके 2 नोड्स आए, लेट अस से सेंस एम्पलीफायर ट्रू, सेंस एम्पलीफायर फॉल्स। इन अ रीसेट स्टेट बोथ विल बी 1 VDD,
यस सर।
है ना? अगर दोनों 1 हैं, VDD पे हैं, देन यू से दैट माय आउटपुट शुड बी held at, my output should not be driven, it is my sense amplifier should be disconnected from the output. Let us say this is the output, so there must be a latch that holds the output, है ना? तो हम क्या करते हैं, हम यहाँ पे एक ट्राई स्टेट टाइप का सर्किट बना देते हैं। PMOS है, जब SAS 1 होगा PMOS ऑफ रहेगा, है ना? और
Yes, sir.
NMOS है, इसके लिए हम SAT का इन्वर्टेड सिग्नल ले आते हैं और उसको यहाँ पे कनेक्ट कर देते हैं। अब क्या होगा, जब सेंस एम्पलीफायर रीसेट स्टेट में है तो देयर इज सम लैच दैट इज होल्डिंग द आउटपुट, वी कॉल दिस आउटपुट लैच और क्यू लैच। ठीक है? बट व्हेन सेंस एम्पलीफायर बिकम्स ऑपरेशनल, देन व्हाट हैपेंस, either SAT or SAF would go to low. Let us say SAF went to low, then what happens, this PMOS will turn on and it will write a 1 onto this latch. Let us say SAT went to 0, it means this would go to 1, so this NMOS will turn on and it will write a 1, it will discharge this node to 0. That is how the sense amplifier output is latched onto the output latch. It is then buffered on Q pin. Are you able to see this?
Yes, sir. So pulse width जो है sense amplifier का वो 100 है, and this Q latch for Q latch purpose we are giving 50. So remaining 50 we have to use for setting this SAT and SAF after read operation during read
No,
operation.
no, 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 no. So sense amplifier का अगर आपने कहा response time, pulse width 100 पिकोसेकंड दिया ना आपने, तो
Yes,
उसका
sir.
मतलब समझते हैं एक बार पहले। सो ये एनेबल सिग्नल है आपका। आप कह रहे हो इसकी जो पल्स विड्थ है वो 100 पिकोसेकंड है, ठीक है? This pulse width is 100 picoseconds. Now SAT and SAF will go here. Let us say to this place, and SAF will go to this place. ठीक है? What we are also saying is that when SAN comes, so this is 100 picoseconds, but SAN arrival to Q latch, either going to 0 or 1, that should be 50 picoseconds. 50 picoseconds दिया हुआ है स्पेसिफिकेशन में।
Yes, sir.
एक मिनट देख लेते हैं।
17।
देख रहा हूँ समय 50 पिको सेकंड दिया हुआ है, तो ये आप ना 50 पिको सेकंड में एक्चुअली बना नहीं पाओगे, तो इसको ऑलरेडी आप 200 मान लो। मैं अपडेट ही कर देता हूँ, क्योंकि 50 पिको सेकंड बहुत टाइट है, नहीं कर पाओगे आप उसमें। मैंने कर दिया, ठीक है, तीनों सेंस एम्पलीफायर्स के लिए कर दिया। So 200 picosecond should be sufficient. Is it clear? Anything else?
सर इसमें ये कॉमन सेंट्रॉइड लेआउट बनाना ऑप्शनल है, राइट?
No, optional है।
नहीं मतलब जस्ट स्टडी बोलकर लिखा था, तो डू वी हैव टू मेक इट इन द सेंट्रल वन?
हाँ, स्टडी इंक्रीमेंटल बेनिफिट मतलब कॉमन सेंट्रॉइड बनाना ही पड़ेगा, और देखना है you have to make 3 layouts over here. One layout is a regular layout without any matching constraints. Another layout is layout with on common centroid matching constraints. Third is common centroid plus structural matching. You have to make 3 layouts over here. Optional नहीं है, 3 बनाने हैं।
सर if I choose this वाला, तो फर्स्ट वो रेप्लिका वाला जो पार्ट था, मतलब that bit lines that we have to make to get
इसमें?
the that वो offset वाला function,
No, why?
मतलब
ऐसे ही आप मान लो कि आ जाएगा आपके पास।
okay.
Why do you need to design the replica path? Design is someone else's job. They will do it. You just design the sense amplifier, but you make 3 layouts of it. But you do it in constraints. Now the sense amplifier width has to be constrained within, this is mux 16. So depending on how the mux is chosen. So IO group has to work very closely knit with each other. Suppose the IO group says that, okay, I will put the sense amplifier below mux 16. Then there is entire mux 16 width that is available to you. Suppose the IO group says, and the multiplexer team says, okay, just so that the delays are not very high, I will implement mux 16 in 2 phases. One is 4:1, and then another 4:1 ka stage. So what happens? There will be 16 lines coming in the top. They will get converted into 2 sets of lines. They will get converted into a 4 set of lines after this 4:1 mux. There would be a sense amplifier for each of these. The outputs of these 4 will then go into this, and you will get the final output over here, single Q. That could be one architecture, or you could say, okay, I will implement entire 16:1 in one go, and then put a sense amplifier later. Typically for high-speed designs, this is what you would do. For high-density designs, this is what you would do. Okay, clear?
Yes, sir.
So this is one step. So are you realizing that the projects are taking you one step ahead of what we discussed in the lectures?
Yes, sir.
So the projects are enhancing your learning from whatever we discussed in the lectures. They are no longer just a repetition of what the lectures told you about. So the learning that you will get in the projects is tremendous. Don't think them as an eyewash. Okay.
Sir, here what is shown in the first configuration, this will be useful for burst operation, right? And matlab we can also
You may do burst, you may not do burst. It's okay, but it will be faster. Why would it be faster? Tell me.
Because the जो mux है उसका वो थोड़ा सा छोटे-छोटे 2 divides है, तो loads will be less.
Yes, the load is only for 4 pairs of bit lines. Over here, there is one big load of all the bit lines. This signal runs horizontally. है ना? It's a huge load, so it becomes much slower. ठीक है?
Yes.
So anything else? Everything is clear.
Sir,
Yes, Anushka.
sir, whatever, so for sense amplifier, so whatever input we give, so we don't have to, design a system to give that input, right? Like in TVD course, I was working on sense amplifier only. So in that case, we gave the sense SAEN as a regular clock signal, and then we kept bitline bar constant, and we incremented bitline bar in steps.
Yes.
Sorry, the bitline.
Yeah.
So will that be enough for testing or simulating the circuit, or do we need to do something else? If suppose
Yeah, so the first part of your project, that is sufficient so that you get the offset. Okay.
Yes, sir. So we measured the offset to be the minimum difference between bitline and bitline bar for which the output was being pulled to either
Yes. So for this
VDD.
part, this is what you are doing. Okay. Just sense amplifier
Yes,
का
sir.
model चालू करके offset निकालना है. But as a part of the project, one of the teams, you will work with them. So you cannot simply sit idle separately. You have to work with all the other teams. See, what is important to realize is, आपको शायद लग रहा है कि आप अपनी एक टीम में काम करने वाले हैं इस प्रोजेक्ट में. In reality, you will realize that you have to work and coordinate with so many other teams to do your project well.
Yes,
Okay?
sir.
So you have to work with the replica path team there, so that they are also able to do their work. So that finally you get the required offset at the sense amplifier. So you will also need to work with them.
So is the idea like after all of us complete our work, so are you like planning to kind of combine all those elements? Because in the project sheet also I saw that all of these projects are part of one type of memory.
Yes.
So in the end, like
Yes,
all the
that's
parts
the
should be able to work with each other.
Yes, they should be able to speak to each other, and the whole memory should be functional.
So ideally, is that the goal of all the projects?
Yes.
Okay, sir.
So no project is happening independently. So the first question in the office hours today was, do I need to make one bit cell or an array of bit cells? So I said, there is nothing like one bit cell in a 8192 cross 32 memory. Na? There is a whole range of memory cells. So there are 512K memory cells that we are talking about.
Okay, so we should be able to also identify what other parts we are directly depending on, so that we can.
Yes.
Okay.
I want you to learn that aspect also.
Okay, sir.
Okay. So anything else, or we can close?
How do we have to select this project now? Like
Yeah. So since we've had this office hours, I will upload the recording also. So others who could not join the office hours, they can have a look at the recording. So I think towards the evening, or then tomorrow after the class, the TAs will open it up for you to register. Okay? We can do it towards the evening. Is that okay with all of you? Or do you need more time to think and discuss?
सर थोड़ा सा ज्यादा टाइम चाहिए.
More time, sir.
So we will do it tomorrow after the class. Is that okay?
Yes, sir.
तब तक आप डिस्कस कर लें अपने फ्रेंड से, बाकी लोगों से. आप देख लें कि कौन कौन सी आप आपस में बिफोर यू एंटर इनटू द शीट, यू एक्चुअली टॉक टू अदर फ्रेंड्स आल्सो, व्हिच यार तुम कौन सा प्रोजेक्ट कर रहे हो. यू फॉर्म बिगर टीम. यू से यार तू भी आईओ में आ जा, तू भी आईओ में आ जा. लेट अस ऑल वर्क ऑन द आईओ पार्ट. So let 2 or 3 teams form a cluster and work on the IO. Let 2 or 3 teams form this, and so do not work independently as just 2 or 3 people, 4 people. Okay, you have to talk to others and set this thing up for yourself. Fine.
thank you, sir.
Yeah, chali. All the best, guys. See you tomorrow then. Bye bye.